So welcome to the Picture Language Seminar on Halloween 2023. We're here in Cambridge, Massachusetts, and especially glad to have Daniel Spielman visiting us from Yale. He's the Sterling Professor of Computer Science, also Professor of Mathematics, Statistics, Data Science, and Director of the Data Science Institute at Yale. He's also the winner of the 2022 or 3 Breakthrough Prize in Mathematics. And we're very happy to hear your talk about discrepancy theory. We're looking forward to it very much. So Daniel, the floor is yours.
Okay, thank you. Cool, so I'm going to be telling you about discrepancy theory and its application in the design of randomized controlled trials. I know this is probably foreign territory for almost all of you or all of you. So please don't be afraid to ask questions, or, the moment I use a notation that is unfamiliar, just feel free to stop me and have me explain it. So there is a paper related to what I'm talking about. It's this paper called Balancing Covariates in Randomized Experiments Using the Gram-Schmidt Walk with Chris Harshaw, who's a postdoc at MIT and on the job market this year, Fredrik Sävje, who's a professor in political science at Yale, and Peng Zhang is a professor in computer science at Rutgers. So to begin, I want to explain why these things should go together. So randomized controlled trials, what you're doing is say you're testing something like a medicine, a medical procedure, a new policy, an educational intervention. What you do when you test these things is you take a group of experimental subjects and you divide them into 2 groups. One you test your new intervention on, and one you treat as a control. And usually you do this division at random. And one of the reasons you do this at random is you want the 2 groups to look similar. You'd like your subjects who are getting the test and getting the control to be similar. Okay, why I felt like this should be related to discrepancy theory is, well, it's about many things, but one of the main results of discrepancy theory is if you have a set of things, you can divide it into 2 sets that are very similar. And how do we benchmark that? Well, usually we say much more similar than if you did it at random. Okay, so if similarity is your goal between 2 groups, it seems like you want to use discrepancy theory. What my goal is to do in this talk is explain to you something about discrepancy theory, then something about how we analyze and set up randomized controlled trials, and then tell you how we can relate the 2. It's not an immediate connection, but it works. And okay, I would like to pretend that I was one day sitting in my office and I saw something about randomized controlled trials and I saw something about discrepancy theory and said, yes, obviously these are related, but that's not what happened at all. So I think the best way to begin actually is to tell you how I got into this. So I have a colleague, Nicholas Christakis, who's a professor in sociology and public health. And he was setting up a study. And he came and he knocked on my door because he was concerned about how it was getting set up. So what Nicholas was testing was interventions to improve maternal health outcomes in small rural villages. This was doing things like trying to come up with ways of getting women to take prenatal vitamins. So he had a study with 176 villages in rural Honduras. I've plotted them as dots here. This is roughly longitude and latitude, so these are their positions. He had 16 different treatments he was trying. So that's 16 different things he was trying to do to improve maternal health outcomes. So if he has 176 villages and 16 treatments, he needs to divide these villages into 16 groups, each of 11 villages. I've colored them based on the treatment that they got. So for example, like all the ones in light blue, we're assigning the same treatment, we're doing the same intervention. Okay, why was Nicholas concerned? Well, they were coming up with different ways of dividing up these villages, and they kept seeing what looked like patterns in the way they were dividing them up. This is what we often call the law of small numbers. And we know if you choose a few things at random, you see patterns in them. So for example, here I take all of the villages that are red. They're all on the western end of this region. And this concerned Nicholas, because he said if those villages do particularly well or particularly poorly in the study, then he's a little concerned. He won't know if it was due to the treatment they got or something going on the western end of the country. Similarly, if I look at all the villages in another group, I divide them up here. And the brown ones, they're sort of all in this middle latitude, same problem. I mean, it's not just that Nicholas would be concerned, but reviewers in particular would say, oh, you know, all those villages are in this one region. Even though you divide it at random, they're going to suggest that this might be a confounding factor. So he wanted a better way of dividing. It was more than that. I mean, this was a big study. So they had gathered a lot of information about the villages that they were going to study. By the way, one of the most important words I learned here was the word covariate, which just means something they've measured about the experimental subjects. So they collected many covariates, like distance to a hospital, time to reach a hospital when it's raining. When it rains, that's a big impact. Median income of villages, average age of people in them, altitude varies a lot in Honduras. All sorts of demographic information and socioeconomic factors. And they wanted to balance all of these. They wanted the model to look similar. And I said, you know what? I can help you because I know discrepancy theory. Okay, so yes.
Their distribution that they showed, that they produced was random by geography only, or was it?
So what I showed there was, so the picture I made was actually just uniformly random, a division into 16 groups of size 11. I only plotted it in the geometry, but oh yeah, we'll talk about that a little more. I mean, I'll show you what we actually did. Although we were concerned about the geometry first. That was the first order thing to worry about. And then the others were sort of weighted. This was an estimation of the experimenters of what was most important. Okay, so discrepancy theory, if you want to learn more, like there are 2 books on it I recommend, either the discrepancy method by Chazelle or geometric discrepancy by Matuszek. There are courses on it online. You can find lecture notes from. I remember there's some by Alexander Nikolov and Peng Zhang. There are probably others by now. So I'll begin by giving you like one example of where discrepancy comes from. This is one of the oldest examples. So imagine, this is not actually about dividing something into 2 groups. This is going to be picking one group out of a continuum. So imagine I have the unit square. And I want to pick a set of points inside the unit square that are representative of the whole. And how do I mean representative? Well, what I'd like to do is I'd like that for every single axis parallel rectangle like this one, it contains about the right number of points. What's the right number of points? The number of points, the fraction of them should be proportional to its area. So here's a problem. I give you the unit square, pick points equal to x1 to xn. You want that for all axis parallel rectangles, the fraction of the points in the rectangle is proportional to its area. So for example, with this rectangle, I have 12 points, 4 of them are inside it, so the fraction is 1/3. If I look at it, I think that rectangle is somewhere around 1/5 of the area of the sphere. 1/3, yeah, it's not that far from 1/5. It's a reasonable approximation. You can ask, how good can this be? Clearly, the more points you pick, the better you can do. Okay, well, I think a lot of people's first reaction is to pick points on the regular grid. Let's do that. And if you ask how well does this do, well, if you have n points in the regular grid, and I take a rectangle that's just a little bit above the midline, let's say, then you get a grid with, well, we'll measure the discrepancy is 1 and 2 at n, where the discrepancy is what is the fraction of points in the rectangle minus the volume of the rectangle. Oh, I wrote volume, I should say area, it's 2D. Okay, take a look at the absolute value. So that gets discrepancy 1 and 2 at n. You can ask, can you do better? But what if I take random points? Random points, it's going to be pretty similar too. If I take the same rectangle, a rectangle with half the area down here, the discrepancy even for that rectangle on average would be about 1 in √2 pi n. So same order of magnitude. Okay, you should still wonder, can we get something better than random? Better than a grid? Yes. So back in 1935, van der Korbut came up with a set of points. So that for all axis parallel rectangles, the discrepancy is at most, well, some constant times log n over n. The key point for me here is log n over n is much better than 1 in root n, at least when n is large. So we can do much better. And that's roughly 10. Okay, so this is one of the oldest results in discrepancy theory. And it's sometimes this is the context. You have a continuum and you're trying to pull a finite set out of it, or a very, very large set and you're trying to pull a finite set out of it. Okay, but what I told you about was taking a particular set and dividing it in two. So let's look at that. This is a, say, a partitioning problem. So I'll give you a set T, could be finite, doesn't have to be. And the target size, let's think f T is finite, so all the circles here. And now you want to find the subset of, let's say half of them, the ones I've colored blue. So that my subset I picked is similar to the original one. How similar? Well, you can say that for all axis parallel rectangles, they contain about the same fraction of points. So I'd say they're similar. If I take any rectangle and I take a look at how many points are contained within it and within my initial set, and we want those ratios to be similar. Okay, let's make this more algebraic because I want to start putting this in a more matrix theoretic language in a moment. So as opposed to describing sets S and T, I will associate a vector. So I'll put 1 at elements of S and -1 for elements of T, and I'll call my vector Z. And to help you understand the way I write things, if I want the jth component of a vector Z, I put it in parentheses. Subscripts for me are names, not indices. Okay, so what I want now, I'll have low discrepancy if for every axis parallel rectangle, the absolute value of the sum of Z over the points in that rectangle is small. That means the fraction of points in S is about the same as the fraction of points not in S. Assuming S, we're trying to make half of the set. This will work. Okay, so I want that piece. This is one of the classically studied areas in geometric discrepancy. However, we can get really nice results for 2 dimensions. It sort of falls off with higher dimensions. So this is maybe not the version of discrepancy we want for my colleague's problem. I mention it because it's a clean one. So let me give you another version of discrepancy that people have studied. We're going to go beyond axis parallel rectangles. But maybe the key pointer is each axis parallel rectangle describes a set. So here I want to describe, we have n people. And then I have a bunch of collections of them that are important. For example, S1 could be the subset of the people who are mathematicians. S2 could be the subset of the people who are computer scientists. These could overlap. Now let's say we're trying to set up trivia teams at a local bar or something like that. And as opposed to letting people be teams with their friends, we want to make it fair. So we're going to divide up the groups. So first thing you got to be sure is you got to have the same number of mathematicians on every team. Otherwise, it's just an unfair advantage. But let's also make the same number of computer scientists in every group. Let S3 be the people who follow sports, S4 the people who follow pop culture, S5 the people who follow music. Okay, you want to divide these teams up so that they're balanced on all of these quantities. So what I want is that for each set, the fraction of people in one group who are in that set minus the fraction in the other, or sorry, the number of people in one group are in this set minus the number of people in the other, that should be as small as possible. Then you're balancing those sets. And we will define the discrepancy of a vector Z that's given plus minus 1 assignments as the maximum unfairness. You know, it'll be really obvious if one of these groups has everyone who's following popular music and one group doesn't have any of them. So you want to make this as balanced as possible. So this is actually the sort of problem that I learned about discrepancy theory first. And people's first reaction is, let's try uniform random Z. How does that do? Well, uniform random Z, oops, okay, so there's a typo on this slide, and I am sorry. But you will show that the discrepancy is probably about root 2n, this should have been log 2d, where d is the number of sets. I wrote an n there by mistake. Why did I write an n there by mistake? Because when people first look at this problem, we often make n equal to d, just make all quantities the same, and it's easier to think about. But I usually want to think of more people than quantities. Then this should be d. Okay, you can ask, can you do better? And there's this amazing theorem of Joel Spencer's, published in a paper called 6 Standard Deviations Suffice. And he shows that you can always get discrepancy in most 6 root d, when d is at most n. There's also bounds for d more than n. Like if d is equal to n, this will be a 6 root n, and you're saving a log. Well, the square root of a log. So you can always do better than random. I should say, if you think too much about it, you might say, huh, you know, is this ever a win? Like if d is equal to n, is 6 actually better than this root 2 log 2n? If n is small, no. But just to defend Joel, if n is small, this isn't 6 either. You know, it grows to 6. But so at least tells us we can do better than random divisions significantly.
But is it complicated to find the division?
Oh yeah, this is an existence proof. So okay, so Joel Spencer's result here just merely proves it exists. It did not come with an algorithm. And for many years, people actually thought that maybe there was no algorithm that was efficient for doing this. Until I was going to put a line down. Okay, it's 3 slides on, Bonsall gave us an algorithm that works in polynomial time. That was 2010. So we'll talk about that in a moment, but let me not forget a few intervening slides. I wanted to put just a little more, I wanted to put this in matrix language rather than set language. So here's how we're going to do that. Maybe I'll state some other results. So I want to let X be the incidence matrix of the sets, by which I mean like X, the matrix, the ijth entry is 1 if person J is in set I, 0 otherwise. And then I can write my discrepancy as I take this vector Z, which has plus minus 1 to every person, I multiply it by X. And the ith coordinate of that is the discrepancy of set I. So now I can write vectors by matrices. And my discrepancy, which we now say is the maximum of the imbalance in any set, that is now the infinity norm of the matrix X times the vector Z, where infinity norm is just the maximum absolute value of a vector, of an entry in a vector. Another way of thinking about this is now for each person, I've made a vector for them that describes them. What it is it indicates for each person which sets they're a member of. 0 if they're not a member of a set, 1 if they're a member of a set. So if I have n people, I have n vectors, 1 for each person, I assemble them into a big matrix. And X times Z then gives you plus 1 for people in one group, minus 1 for people in the other. You can see the imbalances on each group. One reason I wanted to put it in this language is because we can start going beyond 0, 1 properties. And this is important because often, you know, we care about continuous properties. I mean, actually, like if you think about, if I ask you how old you are, you usually give me a number. You don't say old or young. If you look at the protocols in many studies, like the COVID vaccine trials, you were either old or young. You were not a member. Worth mentioning. Okay, so we can actually extend this Spencer result to the case where all the numbers are between -1 and 1. So if I have n vectors with d entries being -1 and 1, still we get the 6 standard deviations bias result. So there exists a z so that the infinity norm is at most 6 root d, which is much better than like the 6 root n log 2d, which is what you would get if you do it at random. And yes, I mentioned Bonsall was the one in 2010 who came up with a polynomial time algorithm. And this really led to an explosion of research in the area. One, because there are a lot of problems in discrepancy theory and people started coming up with algorithms for them. And people kept trying to improve Bonsall's algorithm. And there are many improvements on it because it was polynomial, but not that efficient. And it didn't actually get the constant 6. And you wonder what constant 6 you can get. And it gave us new techniques for solving discrepancy problems. Okay, the first open problem I want to mention is what is the right constant there? Let me mention, even in Joel's initial paper, it wasn't 6. It was a little better than 6. He called it 6 because it sounded better in the title. But yeah, I sort of would like to think that constant is 2, but I'm not sure yet. I would really like to know the right constant.
Why the infinity norm?
It's a somewhat arbitrary choice, the why the infinity norm. It is one that is very obvious to people if you're just looking at discrepancy item by item. Why did Joel suggest doing this? I don't know. You will often find papers in statistics where people actually look at this when they've divided things up into groups and they're looking at the data later and they sort of look at imbalance group by group. But yeah, you're anticipating my next slide, I think, which is we don't have to do infinity norm. We could look at 2 norm. Let's start with that. Let's look at Euclidean norm. This goes back to results of Brown and Greenberg and Beck and Fiala, which are a little older. So they have a result which is algorithmic and very easy. And if we had another half hour, I would tell you the proof. So if I give you a bunch of unit vectors, say n vectors or Euclidean norm at most one in RD, you can come up with a signed sum of them so that the Euclidean norm of the signed sum is at most root d. Okay, this is interesting. If you did it at random and there are n of them, you'd get something depending on root n. So in d dimensions, you can do much better. And it's also nice because you can't improve on the root d term. Just imagine, let's say I just give you d elementary unit vectors. Any signed sum of them is going to have d plus or minus 1 entries. You're going to have norm, Euclidean norm root d. So you can't do any better. And having more vectors doesn't help. I'll just make them all 0 vectors. So I can pad with zeros. So this is a classic result, getting at the Euclidean norm. And you can ask about other things. Oh, I should also mention, you could wonder, okay, even though we know you can do this, and we know there are cases where you can't do better, you could ask, like, if I give you some particular vectors, can you tell if you can do better? So Charikar, Newman, and Nikolov proved that's hard. So if I give you a bunch of vectors where there is a signed sum that's exactly 0, so that sums of both groups are just exactly cancel each other out, you cannot tell if that is the case in a computationally efficient manner. You can't distinguish that from the case where for all signings, the sum has to be at least normally some constant times root d. So while we know you can get to root d and it's optimal, we also know that trying to get smaller is a computationally hard thing, unless you have some nice assumptions about your vectors or something. Okay, you can go beyond this. So I'm going to mention one more theorem of discrepancy due to Banachik, and you'll see why in a moment. So he took a look at the previous theorem and said, okay, that norm, say norm at most root d, that's just a ball. So Banachik's interpretation of the previous theorem was that if I give you a bunch of unit vectors, there's a signed sum, so the signed sum is inside the ball around the origin of radius root d. So what about if I take other convex sets other than the ball around the origin? Banachik's theorem considers any convex set. We need to describe it to be big enough. We use Gaussian measure. That's the probability that a random vector, Gaussian vector, random normal vector, lies inside the set. So the Gaussian measure has to be at least a half. Okay, once you're convex and the Gaussian measure is at least a half, you can hang it hard. So if you take any convex set like that, then there exists a signing. So that, well, okay, I'd like the sign sum to be inside the convex set. It's not quite true, but it's inside 5 times the convex set. That's pretty good. Okay, why was I interested in this? Because, well, there is an efficient algorithm for this by Bonsall, Dushgard, and Lovett called the Gram-Schmidt block. And it's just from a few years ago. They came up with this algorithm, and that's what we are going to wind up using in our paper. So it turns out, and not for any reason related to Banachik's problem that I can tell, but their algorithm turns out to be the right thing to do. And I will explain to you what it is and why in a bit. Okay, so that was my brief introduction to discrepancy. I guess I should take questions on discrepancy if there are some, or if people have things they want to know before I tell you about randomized controlled trials. Yes.
Is it related to the Kinchin inequality?
Yes. So there are, or let's say there are, yeah, Kinchin's inequality is in a related area. Usually people look at that. It's sort of okay, let's just say yes for now. That's probably the right answer. Yeah.
So is it related to some basic problems? Like, for example, if we have an easy model in the paramagnetic phases, and people can use this to characterize how random the spins are distributed around them. This is very similar.
Okay. Oh, right. Yeah, that would make sense. So so interestingly enough, in working on studying things like this, we've spent a lot of time on Ising model and some things that I don't know and I don't think are known yet, but might be relevant. Okay, so if you want to know more about randomized controlled trials, like these are the first 2 books I look at. And there's Rubin and Oh, your colleagues are Nan and Robbins. And let me go back to Nicholas's problem again. Recall I had 176 villages, want to divide them into 16 groups of 11. And why don't I tell you classically how people would do this? So first, let's just think about if we're making two groups. If we're just making two groups, people use an approach we call matching. So what matching says is you divide the villages into pairs that are nearby each other. If we're just worried about the geometry at first. And then for each pair, you flip a coin. So the dividing the pairs, we go matching, you flip a coin. Like if it comes up heads, I'll put this village in group A and that one in group B. If it comes up tails, we do it the other way around. You could do independent coin flips for each of them. There's a way to generalize this to make 16 groups. I mean, if I just told you that, you'd figure it out. What they do is they call blocking. They would make 11 clusters of size 16, like you see here. And then what they do is they shatter each cluster. So again, this is 11 clusters that are close to each other, size 16. So let's say I take a look at this pink cluster. It's got 16 villages. What you would do is then you say, okay, I've got 16 villages here, and I want 16 groups. I assign each of these to a different treatment. So pick a random permutation on those from 1 to 16, do that for every group. This is the classic way to do it. This is actually what Nicholas's group was doing. They weren't doing truly uniform. And I mention this because, in all honesty, the question Nicholas first asked me was not about the randomized controlled trial. He first asked me a question about clustering. He first said, okay, I have these 176 points. How should we cluster them? And because I've written papers on clustering algorithms, but I did one thing that I want to point out you should always do when everyone asks you a math question. Ask him, why are you asking me this question? And then he told me about the design of the randomized controlled trials. Like, okay, let's go for that directly. And so the reason I say this is usually if someone comes to ask you a math question, what they've done is there's something they really care about. And they tried to put it into a language that maybe you can understand, or they think you can understand. And that's very helpful and nice of them. But it's important to actually find out why they're asking you the question and try to meet in the middle somewhere. And sometimes you can make a lot more progress this way. Okay, so let's go back to discrepancy theory. Let's think about making means similar. So if I give you these 8 villages, discrepancy theory does tell me I can divide them into 2 groups with similar means, like looking at the Euclidean norm. This is just a cartoon. I don't know if these are actually means, but I drew like the means of these in the middle. They're very close to each other. But you can ask, does this help if I do the analog for 16 groups? Well, this division has the same problems that Nicholas was concerned with. Like these purple villages are basically in a line. If I rotated this 45 degrees, it'd be very obvious. The orange ones are in a line. While their means are similar, it feels like the distributions are not similar. You might want to make the distributions more similar. And that's why I use the word mean here rather than sum. If I tell you, okay, why not mean is a first order statistic, that's some second order ones, like variances. Okay, I happen to know that if you give me a bunch of points, we can divide them into 2 groups so that their moment ellipses are similar. And that sort of gets you at the second moment. Why do I know that? Because Adam Marcus and Nikhil Srivastava and I proved the Kadison-Singer, solved the Kadison-Singer problem, which gave us a proof of Weaver's theorem. And this is exactly this, or Weaver's conjecture. This is exactly Weaver's conjecture. How similar are the moment ellipses? Well, more similar than if you did it at random, let's say, much more similar. But this is still not clear if this is useful. This is just getting your distributions more similar. Let me just say there are more open problems here than solved ones, and how similar you can make distributions. Why? Well, for one thing, we don't have an algorithm for this. Like this is just an existence result. Even worse, we can't combine this with balancing means, even an existence result. So there's like, we know we can make the moment ellipses similar. We know there's a division that makes means similar. We don't know if there's a division that makes both similar, which is insanely frustrating. Why? Because the 2 proof techniques used are just so different. No one has been able to harmonize them. Okay, so there's a lot we don't know here. And however, while there's no efficient algorithm for this, I've worked on the Cadison-Singer problem for a long time. So I have a lot of code that usually gives pretty good results. So I said, okay, you know, I will help Nicholas out. And I came up with an assignment that balanced everything really well. So geometrically, however they looked at it, they looked at all the marginals and every single covariate, incredibly well balanced. And I said, okay, victory, here you go. And Nicholas was not sure it was okay. So then Nicholas asked me, how does he know this is good? And I said, what do you mean? And he said, well, how does he know that this assignment is not somehow going to be bad for his study? And I sort of said, damn, you're paranoid. I mean, like, I don't know how I would make an assignment that was bad for your study if I tried, let alone why my code would be doing it by accident. Okay, but he was not wrong. So it turns out randomization really is important. So let's think about why. First, at the end of the day, we want to make some formal statement, like it's unlikely these results are due to some unfortunate chance. And if there's nothing random in your study, then I don't know how you would make that statement. We want to do statistics. We want confidence intervals. We want p-values. We want to be able to quantify our uncertainty. And you can't do that without anything random. Also, it turns out, once you realize you're willing to do something random, you can balance things better at random, on average, than you can in the worst case. So you can, random is sort of it helps us. So one way I describe this, I learned eventually that the problem we care about in randomized controlled trials is not really an optimization problem. We're not trying to come up with the most balanced assignment, we're trying to come up with a distribution of villages or assignments that's very balanced on average. Okay, so what did I do for Nicholas? I gave him 100 very different balanced for a random assignment in very different assignments that were all balanced, and please choose one at random, because we didn't have the theory at the time that I'm about to tell you about. But this at least gives you the right idea. You shouldn't just pick one thing that's balanced or low discrepancy, you should have many of them for distribution. And sample from that. Okay, so now I will give you the real mathematical framework we need for talking about randomized controlled trials. I'll tell you about an algorithm. First, let me give you the upshot. The upshot is this thing I'll call the Gram-Schmidt walk design. First is robust, by which I mean Nicholas's fear can never happen. It can never, or it is very unlikely over the randomness that you actually get a bad answer. So it can't be worse than just doing things uniformly at random. But it can be much better. When do we get better? What do I mean by better? I mean, like, we want to estimate how well a treatment works. When do we get better estimates? That's when the covariates are predictive. So when the things we've measured actually correlate with outcomes, then we can get better estimates of treatment effects. So there's sort of two things we want. We want to sort of how to make things better and guarantee that they can never be much worse. And you should explain now really the model, which will help you understand why I've got this language that is a little bit hedgy, because you sort of, I'm always hedging a little, because you never know reality or all of the possible treatments. So we analyze experiments under the Nyman-Rubin model, often called the potential outcomes framework. So for now, let's talk about two treatment groups, a test group and a control group. And for each experimental subject, like a village, we imagine there are two potential outcomes. Little a of I is the outcome if, say, village I assigned to group A. Little b of I is the outcome if group I, village I assigned to group B. The key point, and the reason we call these potential outcomes, is you can never observe both. Like if you do one intervention in a village, you didn't do a different one. So you only observe the outcome of that village. Or let's say, we're testing out, I don't know, let's say we're comparing two medications. You either got one or the other. We never learned the outcome if it was the other way around. We make this assignment at random, and the key point is we assume the only source of randomness is the random assignment. Like, I'm not going to assume response to treatment is random. You can if you want, but it's more conservative not to, and I want to be as conservative as possible, especially when I'm stepping into another field. But anyway, any assignment, let's assume the only randomness is what we do, which is when we assign treatment. when we talk about design, we mean the distribution on assignments. So for example, one opportunity would be uniform. So for each subject, usually I'll just flip a coin independently. If it comes up heads, I put them in group A, tails, put them in group B. That would be an experimental design. Balanced design is one where I pick set A to be a uniformly random chosen subset of half of the subjects. These are not the same because, you know, the first one is not necessarily half. Matching designs, I sort of implied, exist. That's a classic one. You divide the subjects into pairs that you think are similar, and then for each pair you flip a coin. And if it comes up heads, you like assign subject I to group A and J to group B, or the other way, I goes in group B and J goes in group A. Those are sort of the classics. So I'm going to assume for this talk, we're going to have two groups, and both of them will be, for every subject, they'll have a half probability of being group A and a half probability of being group B. So there are these two potential outcomes, but you can't observe both. But here's the problem. We want to measure something like the average treatment effect. This is the average over subjects of what is their outcome if they're in group A minus their outcome if they're in group B. Okay, we were initially thinking about maternal health outcomes. If you're thinking about medical studies, it might be something like how many years do you live if you got some treatment? Group A versus in group B. We want to measure the average of that, we're calling it tau. And of course, the problem is you want to estimate the sum, but it's the sum of A of I minus B of I, but you only ever see A of I or B of I. You never see both. And that's what makes this a hard problem. We're going to estimate it using what's called the Horvitz-Thompson estimator. Just think of it as, if you're not used to this, the sum of the A of I's for I's in group A minus the sum of B of I's for I's in group B scaled appropriately. And the scaling is 2 over N. The reason you scale it this way is it gets you the right answer and expectation. Oh, by the way, important thing though, again, in statistics, when you see a hat over a letter, that means it's an estimator. So tau hat is our estimator of hat. Yeah, right, like now I'm an estimator of data. Okay, so this is right in expectations. I just want to point out this is different than probably your other instinct. Your other instinct is to look at the difference of means of the two groups. You know, they're the same if the groups are the same size. They're different otherwise. The reason I'm using Horvitz-Thompson rather than difference in means is not necessarily right in expectation if the groups can be different sizes. Okay, and then there are things we're going to care about, like how precise is our estimator? What is the probability it differs from the truth by some amount? And then actually we want more than that. In the end, we're not going to discuss it. You want confidence intervals. Like after the end of your study, you need to estimate what was the probability your estimator differed from the reality by too much based on the data that you observe. Okay, let's just take a look at the error. So I want to make a formula for the error. And the way we're going to do it is we again make our vector z, which is +1 for group A and -1 for subjects in group B. And it turns out the error, which is, well, okay, right, is n times tau hat minus tau. It is the inner product of z with a particular vector that I call the potential outcomes vector. It is literally A plus B. So you take A of I plus B of I. That is the coordinate of this vector we call mu of I. And your error is Z transpose mu. And I included a proof here, not because I want to read it, just because sometimes this is counterintuitive to people. So you know there is one. Okay, so this already tells you a little bit why doing things at random is better. Because if I pick Z, a ±1 vector at random, it probably has a small inner product with this vector mu. And I can never know the vector. Like I learn entries A, I learn entries B, I can't learn, but it doesn't matter what mu is. If I pick Z at random, it's probably got a small inner product with mu. Whereas you could wind up in an unfortunate world where if you pick Z somehow deterministically, maybe it's parallel to mu, and then you'll get very large error. Okay, and then there's a question about how do we show that the error is usually small? Yeah.
So is mu fixed because
Yeah, mu will be some fixed vector that we don't know.
Oh.
So we just assume it exists.
But the size of mu is known, right? Like the norm of mu, right?
Well, is norm of mu known? It depends on what you're measuring. Okay, like if we're measuring 0-1 outcomes, like got COVID, didn't get COVID, then sort of the scale is roughly known. Number of years someone lives, scale is pretty well known. But yeah, you do need to make some assumptions about the size of mu. Sort of everything you do is relative to that. So I think it is good to just assume you've normalized mu somehow. Or at least it's known. Okay, so the usual ways you try to show something is close to another. At least in my world, first we usually do it by something like Chebyshev's inequality. You estimate the variance or mean squared error. And if you know the mean squared error, then you can say it's unlikely by Chebyshev's inequality that your actual error is much more than mean squared error. Or if you want to do more, you want to get higher moments. Mean squared error is just a second moment. Eventually, we will talk about estimators where this error is actually a sub-Gaussian random variable, so concentrated more than a Gaussian. And that lets you get tails and things like that. Okay, the mean squared error also has a really nice formula. You get to it by just saying, okay, the mean squared error is the expectation of the square of z transpose mu. You manipulate this formula and take that square, you write it as a product of the same term twice. Then you flip around the terms, so write it as mu transpose z times z transpose mu. Move the expectation inside and you get a quadratic form. So the mean squared error looks like 1 n n squared times mu transpose z mu, where z is the covariance matrix of our vector little z. It's the expectation of z transpose. The reason it's the covariance matrix is that we're assuming z is each entry is probability half of being 1 or minus 1. Okay, so mean squared error is a quadratic form. That's very convenient. But here's the thing. We don't know mu, so we want the mean squared error to be small. We know z, but we don't know mu. So what do? We put an upper bound on it. We say that this quadratic form is at most the squared norm of mu times the operator norm of z, or that's the largest eigenvalue, because this is a positive semi-definite matrix. This is a simple upper bound. And if I don't know mu, but I know z, at least I can try to make the operator norm of z small. And if I can make the operator norm of z small, then I'm good, subject to the scale of mu. So that's what we're going to try to do. And that makes sense because that's at least good in the worst case. I mean, there always is a mu. So the quadratic form is equal to the norm of mu squared times the operator norm of z. So the upper bound can be achieved. So the worst case mean squared error is really captured by the operator norm of this matrix Z. Okay, so now let's take a look at some classic designs. Let's look at the IID design. Each subject is assigned a group with an independent coin flip. If we do that, our covariance matrix, capital Z, is the identity, and its operator norm is 1. And then our mean squared error is 1 n n squared times the squared norm of mu. So, you know, the IID design is really easy to implement, so that should be our target. We should probably do better than that if we want to, you know, argue for something. But then there's a problem. It turns out this is optimal. So if you give me any other design, the covariance matrix Z, its operator norm will be at least 1. Okay, so IID, independent coin flips, is worst case optimal. So if you're wondering then, like, why would we ever use other designs? The reason is that if we give up a little bit in the worst case, we can sometimes do better on average or in the best case. So if mu is somehow nice, or we have helpful covariates that might be informative of outcomes, then we take them into account. Then we can hope to do better. But there is no free lunch. In order to do better under some regimes and some assumptions being satisfied, you have to be willing to do a little bit worse than the IID design. Okay, so now you should ask yourself, like many of us have this intuition, I'd like to make my treatment group and control group the same size. Well, that's a different design. That's picking a uniform random Z so that the sum of its entries is 0. And now you can ask, how does the analysis of that go? Why might this be a good thing? So if I make the groups the same size, I can write down the covariance matrix, and I see its norm is a little more than 1. It's n over n minus 1. So it's a little bit worse in the worst case. What happens on average? Let's look at the mean squared error. in comparison with the independent coin flips model. The leading term, there's a 1 over n minus 1 squared here, where independent coin flips due to 1 over n squared. But then what's going to be in the middle is not the Euclidean norm of mu, it's smaller. So the next term, okay, we'll call for the ID design, I have the Euclidean norm of mu. Here we have the Euclidean norm squared of mu minus its average entry of mu. And this is much smaller than the square root of mu. If the average entries are far from having mean 0. So for example, a lot of things people measure, like let's say years that you live after something, all those numbers are positive. So their mean is going to be far from 0. Okay, now you might be able to do something like guess what the mean will be in advance and then recenter. And then if you do that, the advantages of this start to go away. But if you don't really have a good guess as to what the mean of your potential outcomes should be in advance, then a balanced design can get you much lower mean squared error than just doing IID. Okay, so now let's see how we would use covariate information. Remember I said, if we have covariates and they're correlated with outcomes, then we're going to try to do better. So the best case is where covariates are completely predictive of outcomes. So again, let's have n people, each is a d-dimensional vector. What if this potential outcome vector mu is actually in the span of x? So I can write it as x transpose beta. Then I can expand my formula for mean squared error. I'll put in z, I'll substitute in my formula instead of mu, I'll put in x transpose beta, and I get this expression that looks like this. I get the mean squared error is almost the squared norm of beta times the operator norm of xcx transpose. Now the covariates are things that I measured in advance, so I know them. I choose the design, so I can control z. So I can try to make the operator norm of this matrix small. I won't know beta. Beta is telling me like what is the linear combination that I need of the covariates to get my potential outcomes vector. Now we're not going to be exactly in this case, but it's good motivation. So let's say, oh, sorry, I thought I deleted this slide. Okay, let me go with this one. So here's what we want to try to do. We're going to try to make the worst case good. That is, we're going to try to make the operator norm of z small. We also want to make the operator norm of xex transpose small. Because how small could they be? Well, okay, I told you the two norm of z has to be at least 1. Let's say usually there are a few assumptions, but if the vector is x, it's Euclidean norm at most 1, and some of them are Euclidean norm 1, you shouldn't expect to get this balanced term less than 1, this operator norm of xex transpose. And there's a natural trade-off. So the more balanced you get, the more you emphasize this one, let's say the worse the robustness can become, and we want to know where that trade-off lives and what you get from it. Because let's take a look at a matching design. If you take a look at a matching design, again, you've divided your subjects into pairs. And that means that our covariance matrix of Z is a little block matrix. So these blocks, which are 1, -1, -1, 1 on the diagonal. Many of you are used to block matrices like that. It means we know the operator norm of this matrix in the matching design. It's always 2. Then you can ask, what does the balance term look like? Well, depends on the points, but let's just say if you pick n uniform random points in the unit ball in d dimensions, the balance term will grow like n to the 1 - 2 over d. So it grows polynomially in n. In 2 dimensions, it's good, it's balanced. 3 dimensions or more, it starts growing with n. You can probably gather from my pictures that I don't want that. By the way, an intuitive way of understanding this is there are people who look similar to you, but then once you know more about them, you start to see that they're actually different, right? The more things you measure about people, the more covariates you have, the less it's possible to say, oh yeah, these two people are similar. Okay, when we talk about the Gram-Schmidt walk design, it gives us a trade-off that enables us to keep both the balance and the robustness constant. We pick a trade-off parameter we call phi. You need to pick it before you set the sample. And then you can guarantee that the robustness is the most 1 over phi, and the balance term is the most 1 over 1 - phi. So we get a trade-off that really looks like this. And I should tell you what is the consequence of that for mean squared error. Let me skip the middle and just say what the consequence is the mean squared error has this form. You can actually the most 1 and n squared times the minimum over betas. So there's gonna be like a best linear fit. This on its own looks like the best linear fit of the potential outcome vectors in terms of the covariates on beta, but scaled by 1 over phi. And this is the norm squared of beta scaled by 1 over 1 minus phi. Okay, so if you're a statistician or in machine learning, you recognize this as what's called a ridge regression or regularized least squares. The main thing I want to point out for now is this is just a very nice form of the upper bound that we get for mean squared error, and we can understand this term. So when I say understand this term, think about what happens if you grow your number of subjects. If you grow your number of subjects, mu keeps getting bigger and x transpose beta keeps getting bigger. So this vector keeps getting bigger as your number of subjects grows. On the other hand, beta, which is like the best fit of the covariates in terms of mu, doesn't change, probably. So this would tend to be fixed. This would tell you what you'd want to do is privilege this term and make phi close to 1. And I find that very nice. So that means if the number of subjects grows, you optimize this by actually emphasizing the robustness term. You want to try to make your design very robust, which also means it can never be too bad in the worst case, but you can get much lower mean squared error than the Euclidean norm if your covariates explain your potential outcomes. So I gave you a formula for the mean squared error, but we also get sub-Gaussian tail bounds corresponding to that as the standard deviation or the variance. So, but mean squared error is much easier to talk about than tails. So we'll just talk about that. Okay, so why did this happen? So what Bonsall-Daudush, Garg, and Lovett did is their Gram-Schmidt walk algorithm has the following purpose. This is the description. They say, give me some vectors with norm equals 1. Their goal is to sample a random Z so that this balance term, the operator norm of XCX transpose, is at most, well, they wanted most a constant. Any constant was really okay for them, but 40 is what came out. And not only that, they get that X times Z is root 40 sub X. And this is what they did this because this gave them a polynomial time algorithm for Banachek's discrepancy theorem, well, randomized polynomial time. They show that when you pick this Z, it gives you the signings that put the sign sum inside Banachek's ball with some constant probability. And then you can use that. Okay, so they were all working towards Banachek's discrepancy. And we looked at this, we said, okay, this is great. This is really close to what we need for our problem. The only problem is this 40 or root 40 is sort of bad. Because in our world, that translates to root 40 times a multiplicative factor on, say, the width of your confidence intervals. And I don't know, if I go into a statistician's office and say, I'm going to throw away root 40 on the confidence intervals, I'll be right out the door. So, we spent a lot of time trying to find other algorithms that were better. And then we eventually realized that maybe we can just analyze this one better. So a lot of our paper is actually just dedicated to getting that 40 down to a 1. And it needs a new analysis technique, but it's basically the same algorithm. So you can show that like this Gram-Schmidt walk algorithm solves a problem that sets out to solve with optimal constants, and you can't do better. The other question you might be wondering is, how do we trade balance for robustness? The answer is we don't feed the algorithm the original covariate vectors, we augment them. So let's say the x's were the original vectors of covariance, we stack an elementary unit vector on top of them. Each subject gets their own elementary unit vector. That's how we, sort of like we're trying to balance the elementary unit vectors too. That's how we get robustness. So our input matrix actually looks like a multiple of x stacked with a multiple of the identity. And then we also have to do something which is randomly permute the order of the covariate vectors. You don't need that for the goals of the Gram-Schmidt walk, but it turns out to be important when we compute confidence intervals later. And I will admit that this paper's gone through, keeps growing, unfortunately, but most of the paper right now is dedicated to like central limit theorems and confidence intervals and things like that. let me just say, no, I was going to tell you something about how the Gram-Schmidt walk algorithm works, but maybe I shouldn't, because we're running out of time. Let me just address a few open problems. That will be more fun. So first, you might wonder, can I improve the Gram-Schmidt walk? And I will tell you, our trade-off that we get on that balanced robustness curve is within a constant of what's optimal. You can prove you can't improve it by too much. We still don't know what the optimal is. It comes down to some Diophantine sort of conditions that don't go into the analysis we have. But I suspect the curve we have is optimal. You can ask, like, can you do better if you get samples from a nice probability distribution? Like if your covariates were random? And the answer is, well, okay, there are papers that say you can, but it depends on the probability distribution. There are probability distributions for which you can't. And Peng Zhang, also I should mention, pointed out that it's NP hard to distinguish from the case of whether there is a distribution that gets us operator norm 0 in balance or operator norm at least some constant. So you can ask the question, like, I give you some particular data, can you do better? We know there's no efficient algorithm that's guaranteed to work. In practice, you might wonder what you should do. Well, I'll just say that ideally, I would choose the design after examining the covariates. Like if you get covariates, you can spend a lot of time. People spend millions of dollars on these studies. I don't know why we shouldn't spend a couple $1,000s with GPUs to simulate what would happen with all of our possible outcomes. Makes a lot of sense. You don't just have to use the covariates. You can include functions as the covariates. You can include cross terms in them. You can weight the covariates. A question that I often get is, should we use some machine learning magic or just regression to adjust our potential outcomes we observed and estimate tau hat? Okay, so the risk of this is when you do that, if you have noisy data, you can get estimates that are much worse than what anything common sense would say you should do. And in some sense, we've got a regression in here automatically. So the design itself guarantees that the mean squared error is controlled by this ridge regression, even in the potential outcome vectors. We don't know what they are. We don't know what beta is. You never compute this. It's just sort of regression is implied in the design. Okay, a few open problems. Here's the one that drives me, that I've been working on really like for 4 years. It's the main thing I've been working on. The online version. Okay, in medical studies, people come in one at a time, and you've got to assign them treatment then. You don't get to gather all of your subjects and then assign them treatment. So there's a different sort of problem. We don't know if we can do that. I will mention, well, I'm sure we can. There's a recent paper of Kulkarni, Rees, and Rothfuss that does it up to like something being 10 sub-Gaussian, and they prove there exists an algorithm, but it is not an efficient algorithm. But there's hope. You can consider other relations between covariates and potential outcomes. Anything we say for vectors, you can ask for matrices. So there's a big question, like what's called the matrix Spencer conjecture, where you try to get an analog of Spencer's theorem by using matrix norms. We still don't know if it's true. I'm guessing yes, but it's a big conjecture. And let me just end with my favorite conjecture in this field called the Komlosh conjecture. So that says, if you give me a bunch of unit vectors, Euclidean norm, Komlosh's conjecture is there's a signed sum of them, such that the infinity norm of the signed sum is at most a constant. That's some fixed constant. So this is like Spencer's theorem after you rescale, but Spencer gave an infinity norm bound on each of the entries. Each of the entries had to have an upper bound on their magnitude. This is giving a 2-norm upper bound. It looks a little bit like the sort of thing you would ask with Banachik's theorem, except Banachik's theorem was about a ball of a Gaussian measure at least a half. Here, the Gaussian measure of the ball we care about is like 2 to the minus n. So it's really small. I don't know if it's true. The best lower bound we have on this constant C right now is 2√2, due to Tim Kiniski, who's my postdoc. So he came up with an infinite family of examples where it's at least 2√2, but we don't know more than that. And on that note, I'll say if you want to learn more, well, our paper is on arXiv, and I believe soon to appear, soon to be accepted in JASA. I really hope. We're going through a round of revisions that includes a reproducibility review and other things. And there are packages online for implementing this, and Julia are on GitHub. Thank you. Here, let me go back to the open problems.
Well, thank you very much for a really inspiring, fantastic talk. And I'm sure there's going to be a great deal of discussion. And if there are questions online, would you please identify yourself when you ask the question? So is there any discussion locally? That's contract.
So that's the norm here matter, like if you change the infinite norm to like the L2 norm.
Yeah, so, okay, so for two norm, yes, this is true. Oh, sorry, for two norm, this would be root D, which is one of the theorems I gave before. But, so the infinity norm bound would, around a constant would imply the two norm bound, but not the other way around. But yeah, so if you put the two norm bound there and you put the right thing, then it's easy, relatively easy theorem. But, yeah, the infinity norm is what makes it hard.
I see. Like the other way, like if you do like a special like the Boolean, like a field string, like the x, the vector, like
Oh.
1 minus 1.
Yes, so this is called the Beck-Fiala conjecture, or the natural analog of this, which is if the xi's are 0, 1.
Yeah.
Okay, so if the xi's are plus minus 1, then this is Spencer's theorem. If instead they're 0, 1, and you want to upper bound the two norm, well, usually that means you're saying they're 0, 1, but they're sparse. You only have a limited number of ones. And then there is a conjecture for this, which is called the Beck-Fiala conjecture. And I'll admit we don't know that one either. And it's implied by the Cromlosh conjecture.
But like what's the best like the lower one for that?
Oh, I think that's a good question. I don't know what the best lower bound for that is, but it's probably in Tim Kuniski's paper. He must mention it. There weren't many lower bounds for these things. So, I mean, I for a long time was hoping this constant was 2. And then I spent way too much time coding up some tests and using our supercomputers to look for counterexamples. And I got something that's about 2.001. And then Tim improved those experiments a lot. And that was actually good because then he actually got examples that he could generalize to make a theorem out of. So it's sort of like an infinite family of examples that eventually approaches 2 root 2. But I mean, I'm a believer in that if you can guess the right constant, that might help you come up with a proof. So I keep trying to figure out what are the right constants for these things.
Like back to your previous slides when you have the trade-off between the robustness
Yes.
and the balance. It seems that if they multiply them together, there should be a lower bound for this.
Yes. So roughly the way you get this trade-off is you make X be a tight frame is sometimes the word used in functional analysis. I mean, you want the rows to be orthonormal and the columns to have the same norm.
Is this an uncertainty principle?
I have no idea, but I could imagine it might be.
Yeah,
But-
it's
yeah.
kind of like a
Yeah.
because it seems like you are counting the norm in one like a norm of the original operator, and then you somehow located it, and then
That's right. That's right. And yeah, so you're right. The product of these things is about the right thing to look at for a lower bound. The thing that I really don't know how to take advantage of is the fact that Z is not an arbitrary positive semi-definite matrix. I mean, the lower bounds I do hold for any positive semi-definite matrix with diagonal 1. But the fact that it's actually the covariance of the distribution on plus minus 1 vectors, that I don't know how to put in. If you knew how to put that in, you make it the right bounds.
So is the matrix Spencer theorem a quantum theorem?
Or sorry, I should have said conjecture, but does it have a quantum interpretation? It must, but I haven't thought of it that way. But let me take that back. There is a paper relating quantum information theory to the matrix Spencer conjecture. So probably it is. And they have some results for some regime. I sort of forget exactly which ones they are. But at one time it was one of the state-of-the-art papers. Just from like the last 3 or 4 years.
So do you want to tell us a little about the Gram-Schmidt wall?
Oh, sure. It's a fun algorithm. So what happens is your goal is to find this plus minus 1 vector, which is a point on the corner of a hypercube. And I'll show you roughly the idea of what they do. You start at the origin. And then from the origin, you have to pick a direction. The direction is related to the covariate vectors here, Gram-Schmidt procedure. Let me not tell you exactly how, but you pick a direction. And then you follow that direction as far as you can go one way or the other, so you hit a face of the hypercube. And then once you hit a face, you stay there. And okay, the key point is when you hit a face, one of these coordinates is now 1 or -1. You pick another direction. And then you either go as far as you can that way or the opposite way until you hit another face. You always stay within the face that you were in. So at every step, it's going to set one more coordinate to 1 or -1. It always walks inside the hypercube. The direction is, you have to be very careful how you pick. And you pick your probabilities of going left or right so that on average you don't move. And that enables you to be a martingale that on average stays in the center. So I should say this is very closely related to the Beck-Fiala theorem. That was the one that got us the Euclidean discrepancy theory. But they didn't have anything random going on. They were just getting an existence result. It's also oddly related to something called the cube algorithm, invented by DeVille and Thiel. They use that for survey sampling. So this is like you want to pick out a particular subset of many villages to include in a census. You don't want to use all of them. And it's interesting because if you read their paper, it looks a lot like Beck and Fiala, but they obviously didn't know about Beck and Fiala. And it does things a little bit differently. There's some randomness, and at the end, there's some integer linear programming. So there's sort of two precursors of it. But if you read this algorithm, it seems like it, once you get it, it's sort of just the right thing. I should mention it is somewhat inspired by the algorithm of Bonsall. That was the first algorithm for Spencer's theorem, and other things that came after that sort of looked like an algorithm we call sticky Brownian motion. So they began these algorithms, well, they were not exactly the hypercube, they were working in a different polytope, but they sort of start at the origin and then do Brownian motion until they hit a face. And then once they hit a face, they do Brownian motion constrained within that face, and then they would keep going. So it was inspired, I guess, by an algorithm that looks well, the sticky Brownian motion solves a different problem and looks a lot more complicated. This is actually sort of simple. I mean, there's a little bit of code. Well, okay, you can make better code that's faster, but the naive algorithm is pretty clean.
So are there any questions online?
Hi, can I ask a remote question?
Yes, who's talking?
This is Aram Harrow, MIT Physics.
Oh.
Hi.
Hey, okay.
Somehow I thought you were fully remote, so I didn't even come to Harvard. Sorry to miss you in person. So I'm thinking about some quantum versions of discrepancy, which I'll tell you at another time. But for the clinical trials, do the weights really have to be plus or minus 1? Like, could you have a participant in a trial where they just contribute less to the average? I mean, one question is that ethical? But also, like, would that help if you could?
The answer is yes. Okay, so if you were willing to make some subjects just 0 and not count them, that would help, especially for the online version. But it's not clear it's ethical. And it does feel a little inefficient. So I don't believe it's actually necessary, but in theory, it could be helpful. There are algorithms you could use if you go down to 0 or go with some other low weight. But yeah, people are concerned, like if I'm going to do a study and then I don't actually use the data of some subjects. Well, should they be concerned? That does always happen. I mean, when you do studies, some subjects you have to throw out for one reason or another.
Right.
Some people don't come back to your study or something like that. But I somehow feel like if I, as the mathematician, said the math says you have to ignore some subjects, I'd get some pushback.
Well, you can half ignore them.
Yeah, maybe half ignore them. Maybe say, okay, there's no way just half. Yes.
Put them in with a weight of 0.5.
Yeah, I mean, yeah. So to me, it sounds like a very reasonable thing, but I think it would be a tough sell. And then there is, selling is something you have to worry about here. Because you're going all the way down to like people who are doing actual experiments and they have to want to use the technology. That means they need a team of biostatisticians to sign off on it.
I guess before you even sell it, though, I mean, there's obviously a cost that the variance will go up if you don't use most of your sample. But yeah, I guess is that just from a math problem perspective? Is it interesting from that perspective?
So there's a paper on it from the math perspective. And I'm gonna be really embarrassed to forget the names of the authors other than Yang P. Liu, was it? Damn, I'm forgetting the co-authors on it. It talks about online vector balancing problems. There were two of them. I think they may have, some of them were students at MIT or maybe still are. So, yeah, I mean, they do have a paper that does something like this. If you can make a small fraction of the subject zero, that works in the online case.
Discrepancy minimization via self-balancing walk.
I think it's the one that follows up on that one.
Okay, thanks.
Yeah, good question.
Great. Are there any other online questions? Well, if not, I'd like to thank Dan again for giving an absolutely fantastic talk and for bringing together so many different subjects. I think your many titles are well deserved, and I look forward to the progress